Hello everyone, thank you all for joining me today. I'm very honored to share how to develop BPF tools with like BPF and BPF CORE at Percona Live Europe. First of all, let me introduce myself a little bit. My name is Wenbo Zhang. I come from PingCap, the company behind TiDB, and am an active contributor to lab BPF tools. I was fortunate to get a lot of help from Andre Naglico, who is the BPF and BPF CO-RE projects leader when I was contributing to BPF tools. I learned a lot from him and the community, and I enjoyed communicating with them. Now, let's get on to the topic. I will share my experience about writing BPF applications with BPF. I hope this topic is helpful to those who are interested in BPF and it could inspire them to further develop and improve BPF applications with BPF. So let's see what's BPF CORE first. Before talking about this concept, let's think about what BPF portability is. We know that the development of the kernel is very rapid. Although backward compatibility can be guaranteed at the system core layer, changes within the kernel subsystem do not guarantee this compatibility. When we use BPF for system tracing, we often need to get function parameters, with fields in the struct, and so on. Obviously, BPF projects need to face this compatibility problem. Therefore, we need to clarify the probability of BPF. So BPF portability is the ability to write a BPF program that will successfully compile parse kernel modification and will work correctly across different kernel versions without the need to recompile it for each particular kernel. The solution of BPF portability is BPF CORE. Some people may have some doubts on the necessity of BPF CORE. When we use the BCC, it seems like we didn't encounter any compatibility issues. So why do we need this new thing? The answer is yes, we need it. The reason is that although the emergencies of BCC is a major improvement in the BPF development experience, it has some notable shortcomings. It uses the C-long front-end to modify user-written BPF programs. When a problem occurs, it's difficult to find the problem and figure out a solution. You have to remember naming conventions and automatically generated trace point structures. Because the libbpf library contains a huge LLVM and C-long library, when you use it, you might encounter some issues. When the tool starts, it takes many CPU and memory resources to compile the BPF program. If it runs on a server that lacks system resources, it might trigger a problem. BCC depends on kernel header packages, which you have to install on each target host. If you need to unexported context in the kernel, you have to manually copy and pass the type definition into the BPF code. Because BPF programs are compiled during runtime, many simple compilation errors can only be detected at runtime. This affects your development experience. By contrast, BPF CORE has these advantages. When you implement BPF CORE, you can directly use the BPF library provided by kernel developers to develop BPF programs. The development method is the same as writing ordinary C user mode programs. One compilation generates a small binary file. libbpf acts like a BPF program loader and relocates, loads, and checks BPF programs. BPF developers only need to focus on the BPF program's correctness and performance. This approach minimizes overhead and removes huge dependence, which makes the overall development process smoother. This is why we need BPF CORE and why is the future of BPF. That's the high-level BPF CORE mechanism. BPF CORE only consists of 4 parts: BPF type information, compiler, BPF loader, kernel. I will walk you through one by one. BPF type information, which allows to capture crucial pieces of information about kernel and BPF program types and codes, enables all the other parts of BPF CORE puzzle. What's exciting is that in the latest kernel version 5.11, kernel has been implemented support for model BPF. Compiler provides means for BPF program C code to express their intent and record relocation information. BPF loader ties BPFs from kernel and BPF program together to adjust the compiled BPF code to specify kernel on target hosts. Kernel, while staying completely BPF CORE agnostic, provides advanced BPF features to enable some of the more advanced scenarios. Let's see a hello world with libbpf. As mentioned before, the BPF application is divided into 2 parts: the BPF program that needs to be loaded into the kernel and the control part. On the left part of the figure is a very simple BPF tracing program, and it's triggered when the write system call is initiated. It gets the process ID that triggered the write request and print it out. The part of the write is the stand process. Let's talk more about it. BPF skeleton in BPF app lifestyle. BPF application typically goes through the following phases: open files. BPF object file is parsed. BPF maps, BPF programs, and global variables are discovered, but not yet created. After the BPF app is opened, it's possible to make any additional adjustments. For example, setting BPF program types if necessary, presetting initial values for global values, and so on. Before all the entities are created and loaded. Load phase. BPF maps are created. Various relocations are resolved. BPF programs are loaded into the kernel and verified. At this point, all the parts of BPF application are validated and exist in kernel, but no BPF program is yet executed. After the load phase, it's possible to set up initial BPF map state without racing with the BPF program code execution. Attach phase. This is the phase at which BPF programs get attached to various BPF hook points, such as trace points, key probes, C-group hooks, network package processing pipeline, and so on. This is the phase at which BPF starts performing useful work and read or update BPF maps and global variables. The last phase is teardown phase. BPF programs are detached and unloaded from the kernel. BPF maps are destroyed and all the resources used by the BPF app are freed. So, generated BPF skeleton has corresponding functions to trigger each phase. Name open creates and opens BPF application. Name load instantiates loads and verifies BPF application parts. Name attach attaches all attachable BPF programs. This is optional, and you can have more control by using BPF APIs directly. Name destroy detaches all BPF programs and frees up all used resources. Now we replaced the name with minimal, which looks like the picture on the right. So in addition to these typical phases, there are a few small tips about the phases to share with you. Let's see this. We mentioned earlier that some setup work can be done after the open phase, but if there are no such requirements, we can combine the load phase and the open phase together. The example in the figure comes from the lab BPF project, which is used to measure the cost of autonomy. Look at this one. By default, BPF skeleton will automatically attach all BPF programs, but sometimes we don't want to do this. We'd rather selectively attach certain BPF programs based on command line parameters. So we can attach manually as shown in the figure. This is true from the lab BPF Tools project to detach the delay of the block layer. Now look at this. Earlier, we mentioned that the program can be attached manually, but this has two obvious shortcomings. One is that we load an unnecessary BPF program. In addition, we can't use stand phases well, and the code looks unclear. So the community added a new API to control whether to load the BPF program automatically. This is true from the lab BPF Tools project for starting the delay distribution of some methods in EST4. If this tool runs on the new version of the kernel and supports model BPF, then we choose to load entry BPF program. Otherwise, we fall back to load the capable programs. Look at this. Skeleton is suitable for almost all scenarios, but there is a special case, perf events. In this case, instead of using links from struct name BPF, we need to define an array struct BPF links. The reason is that perf event needs to be opened separately for each CPU. After this, open and attach perf event by yourself. Finally, during the teardown phase, remember to destroy each link in the links and then destroy links. Starting in version 0.2, libbpf supports multiple entry point BPF programs within the same executable and linkable format section. Therefore, you can attach multiple BPF programs to the same event, such as trace points or capable without worrying about ERF section name clashed. For details, see at Lab BPF for support for BPF after BPF cores. Now you can naturally define multiple handlers for an event like shown on the right. Before that, you need to define two different event types for the same event. You may be aware that at present, we have only seen like BPF API related and didn't see that it has anything to do with the portability of BPF. Then we will now introduce some programming concepts related to BPF CO-RE. Let's first look at how to achieve BPF portability in reading structure members. BCC way. BCC will conveniently rewrite task.PID into a call to BPF Probability, which is great, though sometimes might not work, depending on the complexity of an expression used. With lab BPF, because it doesn't have BCC code rewriting magic at its disposal, there are a few ways you can achieve the same result. So if you're using recently added BPF program type tracing BPF programs, then you have a smartness of BPF verifier on your side, which now understands and tracks BPF types natively and allows you to follow pointers and read kernel memory directly and safely, avoiding BPF probe read cores. So you don't need compiler rewriting magical to read the seamless and familiar syntax. Pairing this functionality with BPF CO-RE to support portable, allocatable field arrays, you have to enclose this code into built-in preserve access index compiler built-in. For non-CO-RE lab BPF way, now with CO-RE and lab BPF, there are two ways to do this. One directly replacing BPF Probability with BPF CORE. BPF CORE is a simple macro which passes all the adjustments directly to BPF Probability, but it also makes the Ceylon record field offsite relocation for third argument. By parsing it through built-in per reserve access index. So the last example is actually just this under the hood. You may have a question. If a field has been removed from the structure, is there a way to deal with this situation? The answer is yes. You can use BPF core field exist macro to do this. So how to deal with kernel API changes? Another scenario that causes BPF compatibility issues is the kernel API changes. For this case, BPF CO-RE provides two complementary solutions. Lab BPF provided external key config variables and struct flavors. Lab BPF provides externs a simple idea. BPF programs can define an external variable with a well-known name, such as Linux kernel version, to extract a running kernel version or a name that matches one of key Key configs are keys, such as config hd to get the value of hd that kernel was built with. And libbpf will do its magic to set everything up in such a way that your BPF program can use such external variables as any other global variables. As these variables will have correct values matching the active kernel your BPF program is executed in. Additionally, BPF verifier will check those variables as known constraints and will be able to use them for advanced control flow analysis and that code enumeration. Here is an example of dealing with trace point interface compatibility. After introducing how to deal with BPF compatibility issues, let's take a look at how to pass control information to BPF programs. BCC's approach is achieved through string replacement. Because the BPF program is the string for BCC, it can be modified at will. If BCC is not used, the traditional approach is to write configuration information into the map. This method is not efficient, although the information written in the map is static. The BPF verifier can't recognize this situation, so some optimization can be made. The solution to such a admittedly complicated use case is through using read-only global date. It's set once by a control application before the BPF program is loaded into a kernel. From the BPF program side, this looks like a normal global variable exercise. There won't be any BPF MAC lookup overhead. Global variables are implemented as a directory memory exercise. Control application side will set initial configuration variables values before BPF program is loaded. So by the time BPF verifier will go to validation of a program, configuration values will be well known and read-only. This will allow BPF verifier to check them as known constants and use its advanced control flow analysis. So here is the example. We can naturally pass some filter conditions to the BPF program, such as PID that we want to filter, and so on. Next, let's talk about the storage-related content. Beginning in Linux 4.6, BPF hash maps perform memory pre-allocation by default and introduce the BPF no pre-alloc flag. The motivation for doing so is to avoid key problem and BPF with BPF deadlocks. The community had tried other solutions, but in the end, pre-allocating all the map elements was the simplest solution and didn't affect the user space widthable behavior. When full map pre-allocation is too memory expensive. Define the map with the BPF have no pre-log flag to keep old behavior. For details, see BPF map pre-log. When the map size is not large, for example, is 256, this flag is not necessary. BPF have no pre-log is slower. One advantage of libbpf is that it's portable, though the maximum space required for the map may be different for different machines. In this case, you can define the map without specifying the size and resize it before the load. For example, in the name.bpf.c, define the map as this. After the open flags, call BPF map resize to set the correct max size. Not only you can use global variables to customize BPF program topic logic. You can use them instead of maps to make your program simpler and more efficient. Global variables can be any size. You just need to set BPF variables to be a fixed size, or at least with a bounded maximum size if you don't mind wasting some memory. For example, because the number of soft IRQ tabs is fixed, you can define global arrays to save counts and histograms in soft BPF.c. Then you can traverse the array directly in user space. Furthermore, if you want to know more details, you can read the following articles. The first two articles were written by BPF maintainer, which is very valuable and tells a lot of knowledge related to the principle. The last one was written by me, mainly related to actual compiled. If you want to try it out, you can start with the following two projects, and you can play it after reading this. This is our complete communication. If you have any questions, you can leave a message on this. At last, please let me introduce our company again. PingCap is a software service provider committed to delivering one-stop enterprise-grade database solutions. TiDB is an open-source distributed new SQL database for elastic scale and real-time analytics. That's all. Thank you.